Okay, welcome back. Hello, everyone. Thank you for returning for this next batch of talks. The first one in this session is from Ron Cohen. I peeked into the future, and I saw that this next talk is going to be excellent. So I hope I didn't steal any of your jokes, but yeah, Ron will tell us about MPC with super rushing adversaries. So take it away.
Okay, thanks a lot, Mike, and thanks for the organizers for this wonderful event. This is a joint work with Gilad Asharov, Anirudh Chandramouli, and Yuval Ishai. And before talking about what super Russian adversaries are and all that, I want to first remind people of this Back to the Future movie. And how many here have seen it? Good. Those who haven't, I recommend. So, yes. In this movie, Marty, it's about time travel, and Marty says, well, hey, Doc, what's the harm in bringing a little bit of info on the future? You know, maybe we can place a couple of bets and make a lot of money. And that's exactly what happens in the second movie, when Biff steals the almanac, the magazine with all of the sports results, in 2015, gives it back to his younger self in 1955, and then he creates an alternative reality, a different future, where he gets rich and bets on all of the right horses. And effectively, that's the attack we're going to look at today. And in that movie, Doc tells Marty that, no, Marty, we've already agreed that having information about the future could be extremely dangerous. So in this talk, we're going to show Back to the Future attacks on MPC.
I thought super rushing was cool.
Yeah. And we showed that certain optimistic implementations of synchronous MPC could be vulnerable to those attacks. And the big question here is to understand, given a protocol, whether it's resilient to such attacks or not, whether we can run it optimistically or not. So let's go back to the beginning. When we talk about communication models for MPC, normally there are three main variants. One is fully asynchronous. This is UC, where the adversary has full control over the message delivery, and he can decide whether to deliver a message or not. And most of the UC secure protocols are in that model, and they offer great security in terms of composition, but they don't guarantee termination. The adversary can halt the computation. Another form of asynchrony is the one that Arpita mentioned earlier, and Chenda and Ifan will talk about later on in the workshop. That's asynchronous with eventual message delivery. Here we do have the ability to guarantee termination of the protocol, but it still comes with a price. We don't have what's called input completeness, so we cannot wait for inputs from all of the participants, only from at most n minus t of them. And inherently, we cannot tolerate more than n over 3 corruptions. Now, to answer Evgeny's question from before, the same limitations also hold for partial synchrony. And the third model is a synchronous network where we proceed round by round. And here we can also use a broadcast channel in some of the rounds. Here we get many great results. We have guaranteed termination. We can get inputs from everyone. We can have guaranteed output delivery for anonymous majority, and sometimes even beyond anonymous majority. And this is the setting in which most of the MPC literature is analyzed. And that's going to be the focus of this talk, synchronous protocols. So I'm going to go back to the very beginning of this setting to explain how a synchronous protocol works. So we have a round-by-round structure. Within a round, messages can arrive in different order, but we have a guarantee that all of the messages from a certain round, from round R, will arrive before round R plus 1 begins. And more than that, if a party doesn't send a message, then we can identify. If party 2 doesn't talk to party 3 in a round, party 3 knows that party 2 is cheating. And that's a very clean setting. It's very easy to work with, and it allows us to make some simplifying assumptions. One is that everyone talks all the time. We have all-to-all communication, because we can always add those dummy messages, and we know that this way party knows that others are talking. And we can also assume that the adversary talks in every round. If the adversary doesn't want to send a message, then he can say, I'm not sending this message. Okay, it doesn't change anything in terms of feasibility or the analysis. There is something with efficiency, but let's put it aside for now. So that's many synchronous protocols in the literature are actually considering such a simplified model. Now, there is a great question that Arpita asked earlier. How much time should we wait when we design a protocol? So let's say that the expected duration of message delivery is 1 second. How much time should we wait? One option is to wait 2 seconds. So in that case, rounds are very fast. And let's say an example. After 1 second, 3 messages arrive. After another second, another set of messages arrive. And now party 2 can identify that party 1 is cheating. What's the problem? Maybe party 1 doesn't cheat. Maybe it simply took a bit longer. So if we have the duration to be too short, we can falsely identify honest parties as cheaters. We have another idea. Let's set the duration of a round to be 1 hour. Now, looking back at the scenario from before, we can see that we won't falsely identify slow parties as cheaters. But what's the problem here?
We'll answer in 1 hour.
Yeah, most of the time of the protocol, we simply sit and wait. Right? This is an illustration of people sitting and waiting.
This is why blockchain didn't succeed.
Now, that's OK for certain settings. Sometimes we can really set the duration to be sufficiently large so that with overwhelming probability, messages will arrive. But normally, that's not what we really want. We want protocols to be faster than that. So how much time should we wait? After talking to a few people who implement MPC, I realized that's not the right question. That's not the question they ask. What happens is that we proceed optimistically. After a party receives its messages for a round, it can move on to the next round. So here, party 1 received its round 1 messages. It can move on to round 2. Party 3 now received its round 1 messages, and it moved to round 2, and also party 2, and so on and so forth. Once a party receives its messages, it can move on to the next round. Now, it's not as clean and elegant as it happens in this slide. There's something a bit more dirty that's going on. Because looking back at this setting, when party 1 goes to round 2, it can start sending its round 2 messages. So we have some concurrency between the rounds. Now party 3 moves to round 2, and it can send its round 2 messages. Now party 2 moves on to round 2, and we have some of the parties move on to round 3, and so on. And the protocol goes on like that. So there is something very nice that's happening here. Because we proceed as fast as the network allows us. We really proceed at the speed of the network. Now, before anyone jumps, we're not breaking any asynchrony law bounds. Remember that we assume that if a party doesn't talk, we identify it. Otherwise, there are very inherent limitations that we cannot bypass. So here, when we can identify parties who don't talk, we can proceed as fast as we can. So that's good, right? Can we finish the talk? Right, I mean, looking at that, I'm sure that some of you are asking, wait, what? Because if we have a corrupted party, say party 2 is cheating, then after party 1 gets its round 1 messages, it moves on to round 2. And then it starts sending its round 2 messages, and party 2 received a round 2 message from party 1 before it sent its round 1 message to party 3. And that gives the adversary power that we don't always assume when we talk about synchronous protocols. This is the peeking into the future. And an adversary that can peek into the future, we call it a super Russian adversary. So now we have a hierarchy of adversaries. We have non-Russian adversaries that when they have to send messages for round R, they do it before they see messages that honest parties send them for round R. We have a Russian adversary that can first see the round R messages before it has to decide what to send in round R. And we have super Russian adversaries that can see some of the messages in round R+1 before they have to send all of the round R messages. Yes?
What's the detection rule here for that speaking?
A what?
What's the detection rule for that speaking?
I leave it abstract.
For that?
I leave it abstract. Think that the adversary always talks. If not, we have a timeout for that. I don't protect against adversaries that remain silent. For that, we have the synchrony assumption that we will detect it later on.
It's only one message that you can peek into the future?
If it's all-to-all communication, then it's one round.
So it's
Yeah.
not, it's only peeking one message?
Yeah, for now, yeah. In the future, we also discussed the...
Super duper Russian.
Yes. Okay, so we have a gap. Right? In theory, we assume ideal synchrony. And in practice or in applied research, if we have optimistic executions of a protocol, then the adversary has super Russian capabilities. There's a gap in the analysis. And now the question, is it really meaningful attack? When we take a protocol, will it be vulnerable or not? So the first answer that we show is yes. There is something that's going on here. There are protocols that are secure in a synchronous setting against Russian and breaks when it's a super Russian adversary that can pick one round into the future. So to show this separation, we look at simultaneous broadcast. So here we have 5 parties, 2 senders. Party 1 has message M1, party 2 has message M2. And at the end, we want that everyone will receive this pair of messages, M1 and M2. But other than consistency and validity, we also want that the messages will be independent. Party 1 cannot choose its message as a function of the second input, and vice versa. Okay, and we assume security against one corruption. In this work of Gennaro, Shai, Kushilevich, and Rabin from 2002, where they looked at MPC with 2 rounds, they had a simple protocol for this setting. So in round 1, parties 1 and 2 send their message to the remaining 3 parties, to parties 3, 4, and 5. Then in round 2, parties 3, 4, and 5 echo the messages they receive, and we take as output a pair of messages that was echoed by at least 2 parties. Again, it's very easy to show that in a synchronous model, we have security against Russian adversaries. Okay, if a sender is cheating, it cannot choose its message as a function of the other, and if a non-sender is cheating, it cannot affect majority. And here's a super Russian attack for this protocol. So in round 1, party 2 that's honest will send its message, and party 1 who's cheating will send some dummy message to party 5, say 0. Party 5 received all of its round 1 messages, so it sends its round 2 message. Party 1 received the message from Party 5, which includes the message from Party 2, and now it sends this as its own input. So it can break the independence. And more than that, the remaining 3 parties, Party 2, 3, and 4, don't know whether Party 1 is cheating or if Party 5 is cheating. From their view, they don't know who's the cheater. So that's the first result. There is a protocol that is perfectly secure against rushing in a synchronous model, but is insecure against super rushing. Yeah.
Do you have an example where you violate privacy? Like, say that I don't care about correctness, just privacy.
We can include that as part of it. If there's some event that happens, then I will my input.
Good. And if this is kind of perfectly private protocol at the beginning, so does it work?
Did you peek into the future? Wait, and we'll get to it. We don't have all the answers in this work. Okay, so what's important in this protocol is that we have 2 input providers. That's what the adversary attacked, the input independence. So first, once we have an example of a protocol that breaks, the question is, do all protocols break, or whether we can characterize which protocols remain secure and which break. So looking closer into this attack, what happened is that in the first round, parties 1 and 2 provided the input to the remaining parties in the system. So parties 3, 4, and 5 already learned the output in round 1. And in round 2, they revealed the output. So the attack was that party 1 advanced party 5 into the future, into round 2. Then it picked into its message. It learned the input of party 2. And then it created an alternative reality. And that's exactly the image from the board of Doc in Back to the Future. So we broke input independence. First question is, what happens if there's only one input provider? Right? There are many interesting tasks where there's only one input provider, VSS, broadcast, and the like. So the second result is that in that case, if we have a perfectly secure protocol with only one input provider, then super rushing is equivalent to rushing. And even more than that, it's equivalent to non-rushing. So every protocol with a single input provider that is perfectly secure against non-rushing adversaries is also secure against super rushing adversaries. Okay, and that's nice, and it shows that until now, we had to work too hard. We had to prove security against rushing, and we got too little. We only provided security against rushing. Now we can make the proof simpler, only consider non-rushing adversaries, and get a stronger result against security against super rushing. So that's how it looks. Yep.
So if the protocol is perfectly secure, it can, remain secure even if I know all the randomness of the other parties, right? So in a sense, I can look to the entire future of the protocol and see everything that is going on in the future, and not just super rushing, but super rushing. To the 10th, it's all the same, because even if I know all the randomness of everyone else, I cannot cheat, right? Isn't it true?
Roughly, yeah. So the simulator can guess even all of the randomness of the parties and see if its guess is correct. Yep.
So was the previous result for deterministic functions, one input? Or does it hold for randomized functions? Like
Yeah.
Something like coin tossing?
Yeah, the adversary can guess. It's perfect security.
But it can bias the output, right? Is that, so this is actively corrupt adversary, right? Or is it? So it's a coin tossing. There's a non-rushing protocol where we exchange random bits.
I think it should also hold because it's for perfect security. Right? You don't have any event.
It's a perfectly secure protocol, the other one, right?
Let's take it offline. Good. So with one input provider, we have a nice setting. With two input provider, there's something that's going on. But the protocol that we show doesn't feel like an MPC protocol. Right? There's no privacy. The input provider simply tells their input right at the beginning. And normally in an MPC, we have a committal round. This is a round where up until that point, parties just commit to their inputs, and nothing is learned about the output. And after that point, parties cannot change their input, and the output is revealed. And the question is whether having a committed round provides security against super hashing. So here's a protocol for simultaneous broadcast with a committed round. We'll use the 5-party one-round VSS that's secure against one corruption from GIKR a year before. And in that protocol, simply the dealer does a 1 out of 4 Shamir sharing of its message to the remaining parties. So when we reconstruct, we need 2 shares to reconstruct the value. So here's the protocol. Party 1 and Party 2 VSS their inputs. And in round 2, everyone echoes their share. Now we have a committed round, because in round 1, no single party learns anything about the output. And in round 2, that's the reconstruction. This is what we call an output revealing round. Okay, so we have this nice structure like in MPC. And we still have a super hashing attack. So party 2 was honest, will VSS its input. Party 1 will simply send a random share to party 5. Now party 5 will echo the share that it received. And party 1 has 2 shares now. So it can reconstruct the message, the input message of party 2, and send that as VSS that message now. So it can even VSS it in a way that's compatible with the share that it sent earlier to party 5. So no one is cheating from the point of view of the system. So just having a committed round doesn't help.
Ram, you can have even more strange protocols. You do a commit, then you
Execution, right? If the randomness happens to be the same, simpler. A perfect protocol that with a committed round that breaks. So just a committed round is not enough. Let's see what can help. In the second attack, it was like before, right? It's party 1 advanced party 5, moved it till after the committed round into the output revealing round. Then it picked into its message and managed to create the alternative reality. So here what happened is that the committed round was round 1 and the output revealing round is round 2. So the output revealing round is the round after the committed round. What if there's a gap? So that's the first positive result we have. If we have a gap between the committed round and the output revealing round, and then we can mitigate this attack. Because when we have all-to-all communication, we can pick only one round into the future. So if the adversary managed to pick after the output revealing, that means that everyone completed the committed round. So in terms of the simulation, that means that the simulator first has to simulate the protocol up till the committed round and extract the inputs of the corrupted parties, send inputs to the functionality, and then there are a few rounds that he has to simulate without knowing the output. Then it gets the output from the functionality, and it can simulate the rest with the output. Okay, so that's the theorem we have. If we have a protocol that's perfectly secure against hashing with an asterisk, so we need the simulation to be of some natural form, a way that exists in protocols in the literature. And we have all-to-all communication, and the output revealing round is at least 2 rounds after the committed round. Then we have security also against super hashing. And can we still do something in the previous case? much time? So apparently we can, if the committed round is over broadcast. Because when we broadcast a message, if one party receives the message, that's going to be the message that all the rest will receive. So an adversary that picks into the future cannot change the message that it already broadcast. So as a corollary, we showed that BGW is secure against superhashing. Right? Because in BGW, the structure of the protocol is that first we VSS. The last round of the VSS is the committed round. Then we do the multiplications. And then we have the output revealing round at the end when we reconstruct. So here we have all-to-all communication, and the output revealing is after committed round plus 1. What about linear functions? Where we don't have multiplications? So that also works because the VSS ends normally over broadcast. So we take the extension of the result. And the same also applies for the round-efficient protocols of Benny and others. So those are also remain secure against superhashing. That means that we can actually get stronger security for free. We don't change the protocol at all. And we know that we can run it optimistically. If everyone talks, we proceed as fast as the network allows. And we only need timeouts to identify parties that remain silent. OK, so that's nice. Can we push it even further? What about statistical security? And that relates to what Amos was asking, and also, I think also to what Benny was asking. So we showed that it's more delicate than that. We have a protocol that satisfies all of the conditions, except that it's statistical security against rushing. We have all-to-all communication, and output revealing round is at least committed round plus 1. And we don't have statistical security against super rushing. Right? And it follows from what Benny was saying. We have some event that, in Benny and Amos, we have some event that happens, and a super rushing adversary can amplify the probability of this event. OK. We also looked at sequential composition, and that's also tricky. We showed two functionalities, F and G, and a protocol, pi, that realizes G in the F hybrid model. So it's simply two sequential calls to the functionality F. And we have a protocol that realizes F. And both pi and rho are secure against super rushing. But now when we plug and play, we replace the ideal call to F with an execution of rho, then we lose security against super rushing adversaries. So there's really something that's going on here. So that kind of summarizes what we talked about. And I do want to mention one other result from the literature, the one of Kushilevich, Lindell, and Rabin, that had a generic compiler from synchronous MPC to UC security, to full asynchrony, where we lose the guaranteed output delivery. There in each round, after every party sent its round messages, then it's, after it received all of its round R messages, it sent OK to everyone. Once it received OK from everyone else, it can move on to the next round. So we can take that approach, apply it to synchronous MPC, and get security against super rushing. But that comes with a price of blowing up the round complexity by 2 and adding quadratic communication to the protocol. And the goal here is not to change a protocol to be secure against super rushing, but to look at a specific protocol and check whether it's secure as is. So that's really what we try to understand here. Coming soon, so we have a few other results that are not in the paper. We have other conditions for perfect MPC, where the output revealing round is committed round plus 1, that captures protocol like IKP10, which is a 2-round MPC.
In this case, you need a compiler that only adds one round.
Yeah, that would also work, yeah.
So it will be only additive
Yes.
run an odd event.
Yeah, that's another, yeah, definitely. We do have a sequential composition theorem that bypasses the impossibility that we have. And we also capture protocols where we don't have all-to-all communication all the time, like in Damgard-Nielsen 07, but in those protocols, the communication pattern is known at the beginning of each round. So that we can also capture. And just to conclude, we do show that certain optimistic implementation of synchronous MPC can be vulnerable if we don't pay attention to those back to the future attacks. But we do have some conditions that allow us to run a protocol optimistically and sleep well at night. We do conjecture, though, that most of the protocol, if not all of the protocols in the literature, and that includes statistical security or computational security, will remain secure against super Russian adversaries. So in some sense, this paper doesn't close the question, but it opens many questions to look at. Because I think this is really, can be something nice.
When you say all, you mean general purpose, because
Yeah.
the protocol you attacked was from the literature.
Exactly. Okay, so that's it.
I think we can take a question if the next speaker wants to get set up in the meantime.
Yeah. Can you say what is the form of the sequential composition that you get that bypasses the round?
So effectively, we need a committed round.
I see.
Because once we pick into the second execution, we need to make sure that we don't have the ability to change inputs in the first execution.
I see. Okay, so it's a restriction.